for AC analysis, the first thing I always find is R prime E. R prime E. R prime E is 25 millivolts divided by IP. That's just how the internal resistance here works out to. Okay, so let's see. Was it Dylan who asked that question about 2 times R prime E? Yep. Let's go back to my notes 14 and let's just confirm that. So I'm going to go to page 2 of notes 14. And at the bottom of page 2, AC emitter resistance is R prime E. And then when I go down to R in base, voltage gain, nowhere does it say 2 times R prime E. So for now, I'm just going to work with single R prime E, okay? But that was an interesting question you asked, so I'll do some little background and find out if it is 2 times R prime E or not. Right now, I think it should be just one single R prime E. But what the question is there is an R prime E developed here, there is an R prime E developed here, so is it going to be 2 times? Maybe not. Okay. It's just going to be that one time here.
Oh, I see.
So 25 divided by IE, that's the Q value, which is 68.5. So it's even less than an ohm, isn't it?
Yeah. It's in milliohms.
Okay. Just give me an ohms value. 0 point how much?
0.37.
37. So it's a small value. Okay, so that's R prime E. Now we're going to calculate AV. AV, putting V out over V in, okay, can be, the formula for V out over V in can be expressed in terms of your RE, RL, R2, R1 based on the AC equivalent diagram. So let me take you now to page 3 of our notes 14. Note 14 shows the AC equivalent diagram. And the AC equivalent diagram looks something like this. The DC voltage appears to an AC ground, to the AC signal. This AC signal coming in here feels like the DC source is at ground potential. We talked about that last class, where this DC has basically like a capacitor to ground, and the capacitor to an AC signal is basically a closed switch. So it feels like the DC source is at AC ground. So R1 is at ground, R2 is at ground. So I draw an R1 to ground, I draw an R2 to ground. So this is the circuit that I'm looking at on page 3 of notes 14. Then you've got your transistor circuit with R prime E. You've got your RE. You've got RL through the capacitor, which is closed now. RL. And your R collector is connected basically to an AC ground. So the collector is connected to AC ground, so I show it like this. So that's my AC equivalent diagram on page 3 for a common collector. And I use this for coming up with the AC analysis, which is V in over V out, which is simplifies to the equation shown on page 2, which is RE in parallel with RL. And I can see that right here. RE appears to be in parallel with RL. That's at V out here. And V in is R prime E plus RE in parallel with RL. So there's my R prime E here. And then when I'm looking at the input signal here, it sees this voltage here, V in, okay, and it's R prime E in parallel, in series with R prime RE in parallel with RL. So that's what the V out over V in can be expressed in terms of resistances. So let me do RE in parallel with RL calculation, which is 100 in parallel with 8 ohms, because that's what RL is, a speaker. I'm using RL as a speaker, which is 8 ohms. Divided by 0.37 plus 100 in parallel with 8. How much is 100 in parallel with 8? Product over sum. 7.4, okay? So this is 7.4 divided by 0.37 plus 7.4.
Like 936 or something.
So it's like, is it like 0.9 something?
0.953.
0.95. Okay, so that's my gain. So the gain is actually not a gain, but it's an attenuation. My signal is going to be slightly smaller coming out compared to coming in. So that's my AV calculation, and I can use that value to find V out. So back to my okay, so V out now. Is it AV times V in? So is it 0.95 times V in is 200 millivolts peak to peak. How much?
You're right.
190 millivolts peak to peak.